Welcome to Across the Globe. Today we will learn about support vector machines, SVM. Support vector machines, SVM, are a type of supervised machine learning algorithm that excels in classification and regression tasks. They operate by identifying the hyperplane that effectively segregates data points into distinct classes. SVM aims to locate the optimal hyperplane that maximizes the margin between these classes. For instance, in a scenario where we have data points representing two different species of flowers based on their features, such as petal length and width, SVM helps in drawing a hyperplane that best separates the two classes with the maximum possible margin, thus aiding in accurate classification. Support vector machine, SVM, is a machine learning algorithm that separates classes by mapping data to a higher dimensional space where a hyperplane is used for classification. This hyperplane is positioned to have the maximum margin from the nearest data points of each class, which are termed support vectors. In cases where data is not linearly separable, SVM employs a kernel trick to transform the data into a higher dimensional space, facilitating linear separation. For instance, imagine classifying emails as spam or not spam based on various features like word frequency. SVM can identify a hyperplane in a higher dimensional space to effectively separate these classes, ensuring accurate spam detection. In a binary classification task with two classes, the support vector machine SVM classifier from scikit-learn can be utilized to build a model. The given code snippet demonstrates this process. 1. Toy dataset is generated using make classification. 2. The data is split into training and testing sets using train test split. 3. An SVM classifier with a linear kernel is instantiated and trained on the training data. 4. Finally, predictions are made on the test data using the trained SVM model. For instance, applications of SVM classification include spam email detection, sentiment analysis of text data, and cancer cell classification based on features extracted from medical images. By training the SVM model on labeled data and making predictions on new instances, accurate classification decisions can be achieved. The provided code snippet illustrates a basic implementation of support vector machine SVM for a classification task in Python. 1. Toy data is created using make classification function. 2. Data is partitioned into training and testing sets using train test split. 3. An SVM classifier with a linear kernel is instantiated and trained on the training data. 4. Predictions are made on the test data utilizing the trained SVM model. This example showcases a fundamental workflow of applying SVM for classification tasks by generating synthetic data, splitting it for training and testing, training an SVM model, and making predictions on unseen data. Using SVM is like finding the best way to separate two different groups of students in a classroom. Just like how SVM finds the optimal boundary to separate two classes, we can create a program that finds the optimal line to divide data points into two groups. By adjusting parameters like the margin and kernel type, we can fine-tune our program to accurately classify data points in a similar way to how a teacher arranges students in class based on their characteristics. Hey, Code Conquerors, ready to level up? With TechLearn ATG, showcase your skills with official course certificates. Just visit our site and start. Need that extra boost? Get tailored learning, 24/7 support, and expert guidance. Coding smarter, growing faster, and making learning fun. Go to our website across the globe, www.atg.world. The code snippet begins by importing necessary libraries such as NumPy for numerical operations, scikit-learn for machine learning algorithms, and matplotlib for data visualization. Random data points are generated for two classes, class labels 1 and 1. This data acts as the input to the SVM classifier. A support vector machine, SVM classifier, is created using the svm.svc class with a linear kernel and regularization parameter c equals 1.0. The SVM classifier is then trained on the generated data using the fit method. To visualize the decision boundary and support vectors of the trained SVM model, a scatter plot is created showing the data points colored by their class labels. A grid is then generated to evaluate the model over the entire plot area. The decision function is called to calculate the distance of the samples to the separating hyperplane. Contours are plotted based on the decision function to show the decision boundary and margins. The support vectors are emphasized as larger data points with black borders. Finally, the plot is displayed to show the decision boundary and support vectors visually. The SVM algorithm is widely used in various real-world applications such as text categorization for sentiment analysis, image classification in computer vision, bioinformatics for protein classification, financial data analysis for stock price prediction. The SVM's ability to handle high-dimensional data and find the optimal hyperplane for classification makes it a powerful tool in machine learning. Support vector machines, SVM, are widely used in various industries for classification and regression tasks. One common application of SVM is in the field of image recognition and computer vision. For instance, in the automotive industry, SVM can be utilized for identifying objects in images captured by autonomous vehicles. By training an SVM model on a large data set of images with annotated objects, such as pedestrians, cars, traffic signs, the model can learn to classify new images and assist in decision-making processes for autonomous driving systems. Additionally, SVM is also commonly employed in the finance industry for credit scoring and fraud detection. By analyzing patterns in historical financial data, SVM models can predict the likelihood of default for loan applicants or identify suspicious transactions indicative of fraudulent activity. This helps financial institutions in assessing risks and safeguarding against potential fraud. In both these real-world examples, SVM demonstrates its effectiveness in handling complex classification tasks and providing accurate predictions based on input data. Across the globe, SVM has become a valuable tool in various industries for solving diverse problems and improving decision-making processes. Keep learning, stay curious, and I'll catch you in the next video.